We will look at our all circuits, and there are two. Well, let's first look at it conceptually. So our L circuit, and let's draw a picture that we want to look at. So what we have is a battery, and then maybe a switch here, and a resistor, R, and then we have an inductor, L. We close this off, comes back. All right, so there's that. What will happen in this case is that you close the switch, the current begins to flow, and the current builds up, builds up, builds up until it reaches a steady value. While the current is building up, there's an opposition from the inductor to that buildup of the current. But we know what we should get, conceptually speaking. The graph of the current versus time look more or less like this. There's some kind of an increase. We don't yet know whether this thing, well, it has to tap off at, it's got to reach some maximum value, which you can't push more than the current that the battery can push through a specific resistor. So there's going to be some maximum I. And so this will have to look like an exponential function in that sense. So this is what we should get. And this would be the first type of a circuit where we have current growth. So I growth is the first type of the circuit we have. The second type of the circuit that we'll look at, it's still RL, but this would be current decay. So I decay, current decay. And in this case, what you will have is a setup where you have let me see what I need in here. Yeah, okay. So it's just going to be an inductor and a resistor. So you're going to have an inductor. Now this inductor will have a magnetic field on the inside. There's going to be some kind of a switch and then some kind of a resistor somewhere out here. And then let's just make sure that this is a closed circuit here in that sense with a switch open. So you have an inductor L and then you have a resistor R, and you start with some magnetic field present in this thing. So somehow you managed to charge, not really charge, but somehow you managed to build up a magnetic field in this inductor. And then once you have built up the magnetic field in this inductor, let's see, then maybe you do something like this. Maybe you have a battery here that runs like this. Here's your battery, and you have a separate switch here, right? And when the switch is closed, the current here flows in this little circuit and it charges up this inductor, or it builds up the magnetic field in this inductor. And then you open this switch up. So effectively you remove this little circuit. And instead you close this switch here, and then you use up the magnetic field that is here. So in this case, you would start with some large current, and then this current eventually would decay. And so you should expect something to the effect of, well, you know what you should expect here is that you're going to start with no current, and then this current will build up and it will spike up quickly and then just decay. But we don't worry about that spike in the beginning, and so we will effectively have current that looks like this. And you will start with some maximum current here, and this thing just decays, and you should expect an exponential decay to happen here. So these are the two types of circuits for the RL combination that you should know how to handle. So let's start with the one on the left. And looking at this here, what we have is a certain voltage at the battery. We have a certain voltage across the resistor. We have a certain voltage across the inductor. So I'm going to put here the L, the R, and the B. And we'll just walk around this loop and add up all of the voltages. So let's maybe start, right here before the battery. This is usually what I do, start before the battery, and then I walk around and add up all of the voltages until I end up back here. So what I should have here is I gain the voltage across the battery, so the voltage, there's a plus. I will lose voltage across the resistor, so it's going to be minus delta V across the resistor. Now, when it comes to this inductor, you have to kind of analyze this thing as the current is increasing, because you're going to switch, you're going to close this switch. So you close this switch and the current starts to flow, but the current is going, so there's going to be current here, and this current I is going to increase. So I is increasing. While this current is increasing, the inductor itself is going to oppose that change. So the inductor will set up its own voltage that will point in the direction that is opposite of the direction of the voltage of the battery. So you need to be subtracting this voltage. There's going to be minus the voltage of the inductor equals 0. Now remember that the equation for the voltage of the inductor, I'm going to switch the colors. The equation for the voltage of the inductor is minus L di dt. But you want to make sure that you subtract this voltage and not add it. So that in the next step, what I'm going to write here is that I'm going to have the voltage across the battery minus the voltage across the resistor, that's just I times R, and then minus L times the I t equals 0. I want to make sure that I'm subtracting here, so I'm going to keep that negative. Right, because the inductor opposes the increase in voltage, and so it's going to set up its own voltage that points in the direction that is opposite of the voltage of the battery. So these two, the battery and the inductor, they sort of fight each other. And in that sense, I have to subtract this thing here. Versus in the other circuit, so let's do the parallel section here, the other circuit, we have some voltage across the resistor, and we have some voltage across the inductor. What you have here is that the collapsing magnetic field, as the magnetic field is getting weaker and weaker, that's going to produce a setup where we have a changing flux of the magnetic field through the loops of the solenoid, and that's going to cause the charges to flow. So you will have a positive voltage here across this thing. This is going to act like your battery. So if I'm going to walk around and add up all of the voltages like I did before, so if I start here and I walk around and I add the voltage and I add another voltage here, then what I'm going to end up with is I gain the voltage across the inductor, and then I lose the voltage across the resistor equals 0. So this is what I'll have. And I want to make sure that this is an actual gain. And so then what I'll write here is L di dt minus I times R equals 0. And so this would be good, except that if I follow through with this, I'm going to end up with an equation for I that gives me something to the effect of I equals, I'm going to get an exponential curve that looks like this. And I can't have that. Now it's true that in the beginning I'm actually going to have this. It's going to then spike and hit some maximum and decay, but I want to get rid of the beginning. So here's another way of looking at it. If I wanted to just consider this part, the circuit, then I have to tweak this a little. I know that I need to get a negative in this case here, and there are different ways of looking at this circuit, but here's one. So I want to get rid of this initial spike, and I only want to consider the decay of the current. And so what I'm going to do is I'm going to set it up in such a way that I get that exponential decay. And so I'm going to have L di dt equals I times R di dt equals R over L times L. Now, if I want to get a decay here, if I just want to consider this part of the circuit and I want to ignore this first part, so it's as if this didn't exist here at all, and I want to get the decay, then what I have to do is I have to make sure that I get that decay. In other words, I'm going to add, I'm going to put negative right here. That negative will give me exponential decay, and I'm good to go. That's not the only way to look at it. This is kind of a cheating way, but it'll do the trick. You can analyze it a little differently and end up with the same expression, and then it will feel as if you are cheating less. But be it as it may, this will get you to where you need to go. This is I, by the way. This is supposed to be the current. So then you would solve this equation here on this side, and I guess we'll just, yeah, let's just keep going. So so this will give me di over I equals minus RL dt, and you'll integrate this thing. And on the left hand side, you're going to end up with ln of I plus a constant, put some constant C1 equals minus RL times T plus a constant C2. And so this will give us ln of I equals minus R over LT plus another constant C3, and that gives us I equals E to minus R over L T plus C3, which amounts to being the same thing as I, some constant C4 times E to the minus R over L times T. And then it's pretty easy to see that if you take this function, then you end up with, and you set t be 0, then you end up with C4. In other words, C4 is just this constant here. That's just initial for maximum current. That would be the initial current, but the initial current is the maximum current. This is really the initial current, but we set the initial current to be the maximum, right? We ignore that first spike that we have, and we just study. We ignore this first spike, and we're only interested in the initial I, which is the maximum I. And so now I have my expression for the current here. That's just I as a function of time equals I max times E to the minus R over L times T. And that will do. So we have this circuit. Now let's go back to the other circuit. So so let's see what we can do with this one. So when it comes to this one, what I'll do is well, let's rearrange this whole thing so we can actually make some sense out of it. So delta VB minus I times R equals L di d. And we're not going to pull any tricks on this equation. There's no need, because this one we actually want to consider the whole picture without getting rid of anything. Like in this one here, we're ignoring the initial spike in the current. And so guess what I can do is just go ahead and let's see. Let's divide both sides. Let's divide both sides by L first. So what I'm going to have is delta V B over L minus R over L I equals di dt, and I'll do it because this R over L fraction shows up also on the other side. We had it here as well, and that the time constant. Actually, it's a time constant, the inverse of the time constant. So I suppose what we could do then, well, let's keep going with this equation. We'll play with it in a little bit. So so then what I'll do is I'll do this dt equals, oh, I see now. Yeah, all right. Let's flip this. So what we'll have is, instead I'm going to multiply both sides by R, so I'll have delta VB over R minus I equals L over R di dt. And let's bring this to the other side. So this is R over L dt equals di over delta V of the battery over R minus I is what I have. And so now I can, let's make sure that I have this thing right. Yeah, but let's make this plus minus, and let's put minus here. So on the left hand side, I'm going to get minus R over L times I'm going to integrate here, so that would imply that I'm going to get times t times some constant, so let's say it's c1, and this is going to be ln of I minus delta V of the battery over R, the resistance R, and then plus some constant C2. And then the constants will combine, so I'm going to have minus R over L times T plus some constant C3 equals ln of I minus the voltage at the battery over R. I get rid of ln, so that gives me e to the minus R over L T, this times D, plus C3 equals I minus the voltage of the battery over R, and now we have to keep going here. That gives me C4 times e to the minus R L T equals I. I'll bring this thing to the other side so that I'm going to have here delta V at the battery over R plus all of that. And so I still have to figure out C4. So this is good, but I still have to figure out C4. So current at time t equals 0 is equal to delta V at the battery over R plus C4. But I know that the initial current is 0. So then that implies that I already have an expression for C4, it's just minus voltage at the battery over R. And so in that sense, the expression for the current as a function of time becomes the voltage at the battery over R minus the voltage at the battery over R, e to the minus R over L times T. And then final expression is going, well, not quite yet the final expression, but the voltage at the battery over R, 1 minus e to the minus R over L T. That will do, but then the voltage at the battery over the resistance is just going to be the maximum possible current I could have, which is the current when the inductor is no longer opposing any changes in the current, because the current is no longer changing, it's reached its maximum value. And so in that sense, the current should look like this: the maximum current times 1 minus e to the minus R over L T, and this will do, because we do get the graph we want out of it. So I as a function of time is some exponential increase where you do hit some maximum current at some point, at which point this maximum current is the constant current. I constant doesn't vary anymore, and so inductor doesn't play any role. It's at this stage, it's as if you had a battery here and the resistor and a straight wire, as if inductor wasn't even present. Once you get to the maximum current, then it's just constant. All right, so now what you can do is you can go and, now that we have the equations for both of these circuits, you can go and, there we go here. Now that we have equations for both of these circuits, you can go and solve some of the problems on the worksheet. And the problems are fairly straightforward, I think, but you have the RL circuits, the current decay and the current growth.